I want to introduce you to our speaker. Today, I am so excited personally because we have Luis Vila. He is the structural engineer at GM2 Associates with experience in design, modeling, and analysis of various types of bridges, including steel, arch, pre-stressed concrete, next beams, box culvert, and pipe arch. He also has practical experience in bridge design and load rating, and also preparation of contract plans, bridge rehabilitation study reports, bridge demolitions, and erection analysis, including design service during constructions, among other aspects of bridge engineering. He is also proficient in various structural analysis software, including MIDAS Civil, HTO, BRR, and also Candy. And now Luis Vila is already here joining us today. Hi, Luis, can you hear me right now?
Yes, I can. Can you hear me?
Yeah, I can hear you well. So, wait, give me a second. Yep. Okay. Yep. I think Luis, right now you can also introduce yourself if you want to tell more about yourself, and then after you're done with the introductions, I think we can start the presentation.
Okay. Can you? Am I the presenter already? Can I share my screen?
I will make you the presenter right now, and you can share your screen right now. Give me a second. I think it's still loading right now. Yep, you are the presenter right now.
Okay. Thank you for for that introduction, and thanks again for the opportunity to present this exciting project on this webinar. My name is Luis Vila. I'm a structural engineer at GM2 Associates in Glastonbury, Connecticut. And again, I'm really excited about presenting to you today the load rating of the Gold Star Memorial Bridge in New London, Connecticut. The presentation is going to focus on the planning, the extensive planning that we carried for this load rating, both from a management standpoint as well as organization of the data. Then I'll talk about the modeling, different steps we took to streamline the modeling, and also the validation, the model validation. I'll present a few more examples of the different issues we found during the validation process, and then finalize with a brief description of the gusset plates and gusset and truss members analysis that we did. And after that, we can open it up for Q&A. This is a map of the state of Connecticut. For those of you that are not familiar with the area, this here is New London on the southeast corner of the state, and this that you see here, it's Thames River. So that I-95 going over Thames River is where the Gold Star Bridge it's located. The bridge carries I-95 both northbound and southbound traffic. We did the load rating for the southbound bridge, which is this one, and that's the one that I'll be presenting today. Here's another look at the bridge. Again, this is your northbound bridge, and that'll be your southbound bridge. The bridge is comprised of 30 spans with 3 different types of superstructure, which I'll speak to that in a minute. It's just over a mile long, and combined with the northbound bridge, they have a deck area of about 1 million square feet, making it the largest bridge in the state. The bridge is really a critical bridge to the state of Connecticut, not only because of the large or the extent of the structure, but also it carries a good amount of traffic. So it's really critical for traveling public in the state of Connecticut. Going a little bit more into the different superstructure configurations of the bridge, we have some multi-girder, kind of your typical plate girder bridge on the approach. Then you have some GFS superstructures. And then the main span, which is the one that spans over the river, it's a deck truss comprised of 11 spans. A little bit more detail into the structure breakdown. The first 13 spans are the simple span composite steel plate girder bridge. Then from 14 to 17, you have the girder floor stringers, or GFS systems. You have a two span continuous superstructures there, followed by two span continuous trusses. The main span, which is a 3-span continuous truss, then a couple of simple span trusses, followed by a 2-span continuous truss, and finally ending with a 2-span continuous GFS. The reason for the project is we were updating the load rating to LRFR. We had a timeline of 3 months, which, as you can probably tell, it's a very tall order, very aggressive schedule. I think that's really one of the things that drove us to really focus on the planning ahead of time. So overall, we had 22 superstructure units. That is 22 different models that we built. Just looking, at the magnitude of the number of members that need to be load rated, it gives you an idea of the aggressive schedule that we had. Right, we had to rate the truss members, the floor beam connections, gusset plates, stringers, floor beams, and the girders. So early on, even before we received the notice to proceed, we begin a very extensive planning phase, just to make sure that by the time we received the NTP, we were already set to hit the ground running. The first thing we did was to establish the resources. Right, what's the resource needs for the project? We figured that we would need about 12 people full time for the duration of the project. Now that's a good amount of people. So we needed to plan ahead of time and kind of time it properly to make sure that by the time we hit NTP, we had that 12 people available to work on the project. Once we got the NTP, we started with the data collection and management, which I'll speak to that in a minute. We started establishing the workflows. Once we had a good start on data collection, we started with the modeling. And then when we had a good progress in the modeling, we started with the analysis and the post-processing. I want to expand a little bit more into the workflows, or stress the importance of it. On a bridge like this, you really have to establish the workflows, especially when you're going to have multiple people working on different spans. You want to make sure that everything flows smoothly from beginning to end. And we established workflows right from the beginning, and not only to make sure that everything went well, not only from the production side of things, but also making sure that the workflows were set up in a way that the QC could have been done effectively, and making sure that it was at the end of the day we had a quality product. So going a little bit into the data collection and management that I just mentioned. Just to give you an idea, we had shop drawings itself. We had about 1,800 pages of shop drawings that we had to go through. The same thing, we had a pretty good size bridge plans, original plans, and rehab plans, and a decent size action report as well. So for this, the key here was to treat each superstructure unit as independent bridges, and that was done that way from the beginning, not only for the modeling part of it, but actually how the whole thing was organized, right? So we broke the shop drawings into all of these superstructure units. The same thing with the plans and the inspection report. And the part of the shop drawings associated with the superstructure unit were saved only in the folder where the corresponding superstructure unit. And that was done that way because it was very important for us to avoid as much as possible mixing information from one span or from one superstructure onto another. Something else we did right from the get-go is establishing standard procedures. On a typical bridge, there's not necessarily the need to do that. On a bridge like this, at the end of the day, you have a product that you need to deliver. We wanted to make sure that the product was consistent all throughout, so that things like the dead load calculations or the gusset plate and truss members capacity calculations, that all of that looked consistently and looked the same from span 1 to 30, regardless of who was working on those spans. We also linked the plans and the shop drawings where possible. An example of that is, for example, the gusset plates. The plans will show you just some general details of the gusset plates, but the actual details that you needed to calculate the capacity or to calculate the dead load of these gusset plates, those will need to be found in the shop drawings, right? So we actually, after we brought the shop drawings and the plans into the different superstructure units, we added hyperlinks to the plans. So a person will go to the plans, look at for example, panel point U0. They will click on that, and it would automatically open the file of the shop drawings with the corresponding gusset plate or panel point detail. This was really important for a couple of reasons. First of all, we didn't want somebody to inadvertently use the wrong panel point or the wrong gusset plate just because of having to flip through the shop drawings. And the second part, it's really we had multiple people that needed to access these details, right? Whoever was dealing with the dead loads needed to access this. So if a different person was dealing with the capacity of the gusset plate, they needed to access this, and whoever was checking those things, they needed to access this as well. So with the time constraint that we had, we didn't have the time to really have the people spend every single person that needed access to this having time to familiarize with the shop drawings and where the different things were. So with this, this really helped to whoever needed access to this, they'll just go to the plans, click on this, and then they'll have direct access to the correct panel point. And this hyperlinking and this split of the shop drawings was something that was done in the early stages, and it was QC'd before we could actually started to use it. Something else that we did with the inspection report is, again, may seem like something trivial, but these little things that add efficiently here and there, it's really what helps you in the long run. So we had the inspection report with color coding for the section losses. So for example, the stringers, all the section losses in the stringers were in blue. And the importance of this, it's we would generally task somebody with go to the X span and incorporate all the section losses for the stringers. So that person was able to just go into the inspection report for that span and say, okay, I'm looking for stringers, so I will focus on these 4 section losses. These are floor beams, so I don't have to worry about that. Somebody else will do it later, or that same person will come back to it later. Regarding the standardized dead load calculations that I mentioned earlier, it was done for to maintain consistency throughout the project, but it also helped quite a bit with expediting the QC process. For example, for dead load calculation of the gusset plates and miscellaneous plates at panel point, right? Our engineer will come in, highlight the plates that were considered in the dead load calculations, use the same highlight, the same color to highlight the information in the bill of materials. And then in the Excel that was used to calculate the dead load, we would actually have plate number 1 through 7, but we will actually have the plate ID as it was shown in the bill of materials, right? So for somebody to come in and QC this, basically they will go to the plans, use the hyperlink to get their shop drawings, and they will come to this where everything was color coded and the Excel looked, the input in the Excel looked exactly as it did in the bill of materials, and then they just had to make sure that this matches what was shown in the bill of materials. So this is something that really helped us to make sure that, first of all, we did things correctly, and second, that we had an effective QC process. Something else that we did in the early stages when we were planning this, it's establishing an element numbering convention for all the models throughout the bridge. And this was really important because we wanted our engineers that were working on the post-processing part of the project to be able to, just by looking at the element number, be able to identify where on the bridge they were, right? So that way we avoided multiple people having to go into the MIDAS models just to know what element or what member they were looking at. So for example, if you had a number like this, this would imply that it was a truss element. One would imply that it's the north truss, right? One for the north truss, two for the south truss. The third digit was for the member type, upper chord, lower chord, or diagonal or vertical. And the last two digits was the panel point. So if you were looking at a number like this, you would immediately know that it was a truss element on the north truss, that diagonal member at panel point number 2. Something similar we did with the stringers and the girders throughout the project. Slight differences, for example, for the stringers, we actually embedded the span number in the element number. So this would mean span 14, stringer 12, element 00, so that's the first element, and then it will sequentially increase after that. The same thing for the girders. So once we had a baseline of what we wanted to do and a framework to start modeling, we had to decide what type of analysis we are going to need for each of these superstructures, right? So the first 13 spans, like I mentioned, they were the more typical composite steel plate girder bridge simple spans. So those we did a line girder analysis. The GFS and the truss were more complex structures and really warranted an FEA analysis. So for those, we did an FEA using MIDAS Civil. So when it came to the modeling, it was really important for us to, again, make sure that we did everything as efficient as possible. So while we had the data collection and the calculations going on, we will simultaneously working on developing the CADs and the model templates, right? So the CADs were being developed to eventually import the geometry into MIDAS Civil. We used different levels or layers for the different members, so that way it was a lot easier to assign the structure groups in MIDAS once you import that CAD into MIDAS. Something that I think really helped us a lot to fast track the modeling was the model templates. So you basically, what we did is we created one model template for the GFS spans and one for the truss spans, and these were essentially blank models, right? There were no nodes or no elements. on these models, what they had was the materials and the sections already defined, and you had all the structural boundary and load groups that you needed, and also the construction stages were already set. So once we had those templates, we copied that 3 times for the GFS and 6 times for the trusses, and that allowed us to have somebody put the actual section properties into each of these models while the CAD and the calculations were going on. So by the time you had the calculations, the CAD and the model templates together, it was just a matter of importing the CAD, adding the deadload calculations, assigning the materials and sections to the different elements as needed, and you pretty much had a model. We also use the MCT shells. For those of you that are not familiar with MCT shells, it's a very good feature that MIDAS has, where it basically allows you to export any model as a text file. So you can take different chunks of that model and actually create a template, if you will, right? So we use that for the vehicle libraries and for the moving load cases, where we created the vehicle library and moving load cases using the user interface for one of the models, and then we exported that to the other models, right? So the good thing about that, again, looking in terms of fast tracking the production in the modeling and the QC, the good thing about that is once you create that template and you QC it, there's no real need to QC that on every single model. So the only thing you have to make sure is that to check that they were imported correctly. So the engineers didn't have to define every single vehicle on every single model, and at the same time, the checker didn't have to check every single vehicle on every single model. When it came to modeling, we really had two main challenges. The first one is consistency in the modeling, given the fact that we had a lot of people working on different models. Those we addressed by the pre-planning and establishing the workflows that I just mentioned. The second main challenge was really the model validation. It doesn't matter how experienced of an engineer you are or how many models you have created. In my view, validation is really part of the QC process, and every single model needs to be validated, because subtle differences between superstructures, geometry, and links could really make a model behave different from another model, right? So we did a validation of these models. I just want to bring a few of the issues that we noticed and we corrected during our validation process. The first one being, we looked at the bending moments on the stringers, and we noticed that it didn't look quite right. You have like a sudden jump from positive moment to negative moment. So it was clear that there was something going on. Also, the magnitude of the moments were really high. So we took a closer look to see what might be the cause for that, and we figured that there were two factors that were really affecting that. The first one was the rigid links that we had from the stringers to the floor rim. We had all the degrees of freedom constrained, and that combined with the deflection of the truss was basically inducing unintended additional bending moments to the stringers. Hence the jumps or the jumps that we were seeing in the bending moments. So the immediate first solution that we thought of is, if that's the issue, then we can just release the rotation degree of freedom on the rigid link. However, our structure or our structure in the model was not aligned with the global axis, so we couldn't really do that. The reason for that is, we developed our CAD exactly as the bridge was shown on the plans with the working points and everything, because that was really, the most effective way to make sure that we got it right the first time around, and it also helped expediting the QC process. So once we noticed that, okay, so it's not going to be as straightforward to just release that one. So what's the other factor that was causing the issue? Okay, so well, the deflection of the truss. So we actually decided to remove the truss from the model, and just for the analysis and load rating of the stringers, we had the models without the truss, and we added supports to the floor beams at the locations where you would have the truss. After we did that, then we essentially corrected the bending moments on on those stringers. The second issue we corrected was we noticed that in one of the GFS spans, one of the floor beams was picking up a large negative moment at the connection with the main girders. As you can see here, most of the floor beams have about the same magnitude of negative moment at that connection, but this one was really high. So we took a closer look at what may be causing that, or how could we correct that. This is what the connection looks like, or what the typical section looks like at that span. Looking at it, we have the knee brace here, which we did not include in our initial model. Again, just to simplify the modeling. So we decided to, what if we do a more refined model to see what is the actual behavior of this connection, right? So we created a localized refined model where we use plate elements for the webs, and we also included the knee brace into the model. So the refined model has, that's the typical section of the bridge, what the refined model looked like. So once we had that refined model, we went back to our initial model and added a series of links to simulate that knee brace. And we calibrated the stiffness of these links to match the results from the refined model. And this is what it ended up looking like for one of the load cases. The original model had a negative moment of about 1,800 cube feet. The refined model reduced that to about 1,100, and then the calibrated model with the links, we modified it to match as close as possible the 1,100 cube feet of the refined model. The last validation example that I wanted to bring is bottom port of one of the trusses. So this is what I mean, with where I see the importance of validation. We had 6 different truss models. Out of the 6 models, we only saw this issue on this one model, right? So we noticed that the moments in the bottom chord were not, both from a qualitative standpoint as well as the magnitude, were not what we were either expecting or seeing on the other spans. So we actually spent a good amount of time trying to figure out this one. Luckily, it was a simple fix. What happened was that out of all the truss members, these diagonals here were inadvertently modeled as sent with the insertion point as centered up. So that eccentricity of the insertion point was causing the irregularities in the model. Once we fixed that, we changed that member to have a center, insertion point. And once we did that, we went back to the expected bending moments and much more realistic magnitudes, similar to what we were getting on the other spans. So my hope with this is that you see the importance of validation. A lot of these issues were really picked up because of our detailed validation process. So again, I can't stress enough that validation, it's really part of any QC process. Moving on to the analysis of the gusset plates. This was perhaps the most challenging part of the load rating, because we had a very large number of gusset plates. We wanted to make sure that we were doing this in the most efficient way possible. We looked at 11 failure mechanisms, basically the applicable mechanisms from the MBE. So when we started this, we were thinking, is there any way that we could set this up such that we don't have to look at 220 capacity worksheets line by line to make sure that everything was input correctly, right? So we end up coming up with the approach of having one Excel file for each superstructure unit, and that Excel file will have all the inputs that you needed to calculate the capacity of the gusset plates. And then we created one capacity calculation worksheet, and that was done early on in the project, and that got QC'd. And once we were sure that that was entirely correct, then we proceeded to copy that 220 times, right? The good thing about this is that we didn't have to check the inputs in all of these 220s because we already had that Excel. So those 220 capacity worksheets were pulling the information from this Excel. So the QC process for these worksheets was really going in and making sure that it was pulling the values from the correct panel point in the Excel file. The other challenging part about the gusset plate was really the fact that we were load rating them based on concurrent member forces. So to get that, basically you have to use the MIDAS feature of the moving load tracer, right? That feature basically lets you tell MIDAS, hey, I want to know what is the vehicle configuration that causes maximizes the axial load on this member, right? And MIDAS will show you something like this, and it will also allow you to create what we call an equivalent static load case. So this load configuration can be converted into a static load case, and then you rerun your model for that static load case, and that will give you the member forces on all the other members for the load case that maximizes the load on that member. The challenge, again, given the large size of the bridge, the challenge was that we had to create over 80,000 static load cases to load rate these gusset plates. Right? Luckily, MIDAS has a feature that's called batch conversions, that it lets you tell MIDAS, I want to generate the static load cases or the equivalent static load cases for all of these members, and it would pretty much automatically do it. The problem with that, or the risk that we saw with that, is that there were so many cases that we didn't want to just run it off of one model and spend 2 or 3 weeks generating those static load cases and have the risk of something happening during that time. Whether we lost power or the computer crash or something else that could have basically stopped the process. At that point, you were back to square one, and you had to start from zero to generate that. You're resetting the clock. So we split the models into different multiple models to generate the equivalent static load cases. That also allowed us to run it on multiple computers, and even then, at its peak, we were looking at 12 computers running 24/7 for about 2 weeks to generate these static load cases. So that shows, here comes the importance of a proper standard workflows and proper QC process, because the last thing we wanted to happen is, you spend 2 weeks generating these static load cases, and then you realize that, oh, there was something wrong with the models. We have to rerun the live load analysis and rerun this for another 2 weeks, right? That could really throw the schedule of the project out the window. For the Truss ratings, we did something very similar to the gussets, in the sense that we had an Excel with all the inputs needed for the capacity calculations. We have one capacity templates, and that ended up being copied over 300 times. We also use concurrent member forces to load rate the Truss members. Luckily, the same equivalent static load cases that we use for the gussets work for the Truss, so we only had to do that once. Overall, the project was a success. The key factors that contributed to the success of the project, extensive project planning, trying to foresee what were the different issues that we were likely to encounter. The validation process, again, can't stress this enough, really, really key in any project. Establishing workflows was really important to make sure that everything was done consistently by the different people that were working on the project. Execution, it really takes everybody, working at their best to get this done, right? You can plan as much as you want, but it really takes a good team effort to execute properly and get you to the finish line. And last but not least, having a very good QC process and model and establishing workflows with QA and QC in mind. So with that, I'd like to, special thanks to the Connecticut Department of Transportation. We are really appreciative of them giving us the opportunity and having the trust to give us a project this challenging and this critical. Also, MIDAS for setting this, putting this webinar together, and also the technical support that they provided during the course of this project. Last but not least, hats off to the GMT load rating team. Like I said, it really took everybody working at their best, and a really good team effort to get this to the end line. So with that, I'll open it for any questions that you may have.
Okay, thank you so much, Luis, for the presentations. It was really insightful. And I think for everyone, just like Luis Vila mentioned, MIDAS Civil has a lot of powerful features. I think Luis Vila has explained some of the features that we have. One of them is the MCT shells feature in MIDAS Civil. With that feature, you can save a lot of your time when it comes to doing the bridge project. And I think if some of you haven't used MIDAS Civil yet, I think this is the perfect time for you to talk to our team and then find the best solutions that our software can help you with your project. But Luis, thank you so much. It was really insightful. And I think right now we can move on to the Q&A session. Guys, you can type in your questions right now in the question bar, and we will be discussing it in a few minutes. But before that, I want to ask a quick poll to you guys. Give me a second. Okay. So in MIDAS, we always want to improve our service and also the quality of our content, right? Including our webinars and also workshop. So in In order to do that, I need you guys to answer this quick question about the satisfaction levels. Only one question, it will be quick. So yes, please answer the questions so we can improve our service and our content in the futures. And while we are waiting for all the attendees to fill out the poll, just for your information, our expert engineers, which is Luis Vila, our speaker today, recently Luis Vila and also GM2 Associates, they won the 2021 CSCE ACE Award for Excellence with Innovation Technologies for their bridge rehabilitation project in New Haven, Connecticut. So once again, Luis, I want to congratulate you. We are so happy with your achievement and with GM2 Associates achievement, and we are so proud to have you as one of our expert engineers.
Thank you so much.
Yeah, of course, it's our pleasure. And also, you mentioned about the technical team. It's also our pleasure to help GM2 Associates. We've been having a really good relationship, and hopefully we can, always support you and also your team and GM2 Associates in the future. And I think right now we have a few questions so far, and I will play it out in a second. And I think almost 80% of the attendees have filled out the poll. Guys, please fill out the poll so we can improve our service and also we can improve our content quality. Okay, I will pull up the questions. So far we have, okay, give me a minute. I will put all the questions into one slide. Okay, I think we can start with the first 5 questions. And then my team will put more questions to the PPT right now. Okay, Luis, can you see my screen right now?
Yes, I can.
Okay, yes. The first question is actually from our expert engineer too, Amir Botras from Stantec. So typically, truss members are designed for bending moments for their self-weight only. What modification did you implement in the model to introduce the concept of pin gusset connections rather than rigid gusset connections and eliminations of bending moments generated from the other load cases?
Okay, let me. Right. So we did not look. I guess we didn't have pin connection at the gusset plates because the detail on the bridge basically had the top and bottom cords as being continuous, right? So in addition to having the gusset plates, you had additional external and internal splice plates that were essentially making the top and bottom cords continuous. So we did have the moments at the panel points, the top and bottom cords. All right. So do you want me to go to the second question or? Tito, can you hear me?
I'm so sorry, Luis. I was muted. My bad.
Oh,
but
okay.
yeah, I think we can go to the second questions from Alberto Alvina. So he was asking about what kind of panel connections that the existing truss have. Are they bolted or riveted? Also, what boundary conditions were assumed at these panel points, pin or fix?
Okay, so yeah, I think that it's probably kind of in line with what I mentioned. Can you show the question?
Yep. Give me a second. I just need to edit the PowerPoint. Yep. Can you see the question right now?
Yes. What kind of panel point connection the Deflection Truss have? So yeah, so basically these are bolted, well, a combination of bolted and riveted gusset plates, and basically the top and bottom chords were continuous. The diagonals were assumed to be pinned at the ends. So basically, we had a combination depending on the detail of the member. We had a combination of either fixed or continuous through the panel point or pinned at the panel points. Generally, top and bottom chords were fixed at the panel point or continuous through the panel point, and vertical and diagonals were just pinned.
Okay, thank you so much. Next question from Cho Yu Yong. Any particular reason why you did not consider using envelope forces for the gusset plate rating?
Yes. So basically, what happens is depending on the failure mechanism that you're looking to, you're looking to lower your gusset plate. Having envelope forces may not necessarily always be conservative, in the sense that if you're looking, let's say, at the left side of the gusset plate, where you have your bottom chord and you have your diagonal coming in, there is a potential for the load on that diagonal to, you're looking at the maximum force on the bottom chord. There is a potential for the load from that diagonal to act opposite to the one on the bottom chord, right? So you really, for gusset plate analysis, you really want to make sure that you do a concurrent force. You base it off of concurrent forces to make sure that you're looking at the actual loading condition and you're not, underestimating or overestimating rather the capacity of the gusset plate, or underestimating your loads.
Okay, thank you so much, Luis. Next question from Mario Lococo. It seems member capacity rating calculations are performed by spreadsheet instead of MIDAS. Is it?
Yes, correct. So we use a worksheet. Basically, we use MIDAS for the modeling and the structural analysis, but the actual rating and everything else was done, post-processing outside of MIDAS.
I think that also answers the fifth question, right? About load rating function of the program wasn't utilized.
Correct. Yes.
Yeah. By the way, Luis, is there any specific reason why you didn't use the load rating function in MIDAS Civil?
Yes. As of now, my understanding is that MIDAS doesn't have the function yet to low rate non-composite members. So everything in our bridge, including the stringers, were non-composite. So for that reason, they were low rated externally.
Oh, I see. Actually, we also have our theme today right now. Xiaofeng, can you add more explanation about it, about the load rating function in MIDAS Civil?
Yeah, I think Louis was right about it. Like for the non-composite session, it may need to run the structural analysis first, and then do some like external spreadsheet work to have the final rating design.
Okay, I see. Thank you so much, Luis and Xiaofeng. And I will refresh the PowerPoint. Give me a few seconds. Yep, we have so many questions today. Luis, the next question is from Opio Hunter. How long did the modeling and load rating portions of the project take?
I don't know. The overall project took about 3 months. We really, I think I would say for the first, I don't know, the first few weeks, the first month, we were just setting the or organizing the data, and basically breaking the bridge down into smaller pieces. So the whole modeling, it just kind of, everything was kind of blended in. We had a lot of overlapping tasks, but I would say, if I had to say something, I would say about a month and a half. But again, we had the modeling going. Before we were done with the modeling, we were, with the modeling of the full bridge, we were already starting the post-processing of the spans that we had modeled. So it's kind of hard to give you a definite answer on that.
I see, totally understandable. Next question is a follow-up question from our expert engineer, Amir Botros. Experience has indicated that releasing the moments at the ends of truss members usually result in instability problems. Any recommendation for that?
Yes, that's a very good point. Basically, yes, if you have a truss completely modeled with truss elements or completely modeled with beam elements, with beam and releases, yeah, generally you will get instability issues. In our case, we did not have the issue because we had the top and bottom chord were continuous. So the rigidity or the stiffness of that continuous top and bottom chord really helped with the instability issues. In the past, sometimes you have to see what's causing the instability. Sometimes you could add, things like adding lateral supports at the panel points, which doesn't really affect the the vertical behavior of the model, but it really sometimes that helps you with the instability on the out of plane behavior of the model. But luckily in this case, we had top and bottom chord were continuous, so we did not have that issue here.
Okay, thank you so much. Next question from Yiming Lan. Was MIDAS used for computing capacity and set up for load ratings? Hello, Luis, can you hear me?
Yeah, sorry, I was muted.
Okay.
Yeah, I think this goes back to the other questions. No, MIDAS was only used for the modeling part and the structural analysis part of it.
Okay, yep. Next question from Mario. Did Connecticut DOT request proof calculation for the analysis result by MIDAS?
I am presuming that the question has to do with the structural analysis. If so, the answer is no. But again, that's something that we did validate not only with the samples that I brought up, but also we have to validate it in terms of, are we getting the member forces that we're getting, are they making sense? Are they within what we're expecting? But no, there was no proof calculations for the analysis.
Okay, thank you. Next question from Jin Zhang. In the stringer only model, what was type of the support placed under stringers? Does truss flexure rigidity affect lateral distributions of the live load among the stringers?
So we used we still had the rigid link connecting the stringers to the floor beam. What we did is at the location where the floor beam connected the truss, we just added pin supports at that location. Okay, so the second part of the question: does the truss flexure rigidity affects the lateral distribution of the live load? So my answer to that is it kind of depends. If the two truss lines have the same stiffness, then you're not likely to have your live load distribution affected. If for some reason you have a good amount of difference in the stiffness of one truss line versus the other, then yes, it is likely that you'll have more effect in the life load distribution between the stringers.
Okay, thank you. Next question from Jian Tao. I think it's like a statement, but also a question. It is important the offset is center to center for all truss members, right?
Correct, yes.
Okay. Next question from Payment Azarmina. If you didn't have any time limitations, what was your suggested time for this project? But yeah, if you didn't have any time limitations, what was your suggested time for this project?
Yeah, I don't think I can answer that. I think every project comes with its own time limitations.
Yeah,
and you need
timeline.
to assign the resources that you need to meet that timeline.
Yeah, that's true. But yeah, Payment, I hope that answer is clear enough for you. Next question from Sadiq Mahmud Hani. I was wondering if you considered installing any kind of sensors on the bridge to validate the model.
That would have been pretty nice, but no, I don't know that was ever considered. It's a really large structure, so I don't know that beyond the fact that it would have been nice to do. I don't know that would have been on we actually needed to do that.
Okay, I see. Yep. Next question from Francesco Ricitelli. To validate the results obtained from the MIDAS modeling, have you used other design software to compare results? If so, can you give an example? Just use MIDAS, guys. Yeah, but yeah, Luis, you can answer.
Yeah, no, we I guess I mean what happens is when we normally use MIDAS basically for bridges that other softwares can handle. So most of our validations are just qualitative validations in terms of are we getting deflections within what we were expecting? Are we getting the member forces within what we're expecting? Sometimes we do, we make sure that the load paths that we have is what they should be, right? If I applied a load to this member, we are expecting for it to be distributed a certain way. So we look to make sure that that the model it's doing what we are expecting it to do.
Okay, thank you. Give me a second. I will refresh the PowerPoint. Okay. Next question from Choyu Yang. Was construction staging being considered?
Yes, all of our model had construction stage considered.
Okay. Next question from Stephen Smith. Was the load rating analysis performed using MIDAS Civils built-in load rate? I think these are the same questions like the previous questions, right?
Yes. Yeah.
I think we can skip this. Was an influence diagram or surface considered for the double L analysis from Jared Tully? Yep.
Yes. So yeah. So the moving load analysis that MIDAS does, it's based on on generating influence lines for essentially all the elements that you have included in the analysis. So yes.
Okay. Next questions from Yiming Lan. How the critical load ratings are summarized and members located, and were the deteriorations accounted?
Okay. So I'm not sure I understand the first part of the question. How the critical load ratings are summarized.
Yeah, I think there's like some words missing in this question.
Okay. The second part, yes, the deteriorations we accounted for them. We early on we marked up all the section losses in the inspection reports, and then once we had the models and we included those deteriorations in the post-processing stage.
Okay, next question from Jackson Eno. This bridge has several travel lanes and wide shoulders. Were actual strip lanes used to curb for live load forces?
So we used, we're doing LRFR, so we basically followed the AASHTO LRFD code and the MBE, meaning that if we define the travel way from curve to curve, and determine the number of lanes based on the actual design lanes. Tito,
sorry guys,
are you muted?
Again? My bad. Next question. Follow up the rigid gusset plate connections. Since the top chord and bottom chord are assumed to be continuous, can you clarify how you consider the moment in the gusset plate or chord splice rating? From Cho Yu Young.
Yes. So basically, I think the MB has some provisions to that, but basically, you have the moments or the member forces coming from MIDAS. You'll have all that information. Then all the plates that are crossing the splice plane, including the gusset plate, get accounted into the stiffness and the capacity of that chord splice rating.
Okay, thank you, Luis. Next question from Srikota, our loyal users. Can you speak of the results? Were any members or gusset plates found to be critical that need rehab?
Okay, so no, I appreciate the question. Right now, first of all, off the top of my head, I really don't recall the ratings or the results. So I really can't speak to that. And we're also still making some refinements. So at this point, none of the ratings are really finalized. So yeah, I really can't speak to that.
Okay, yeah, that's totally fine, totally understandable. Next question from Biku Khalifa. You modeled as continuous member. How did you take care of the splice in plates?
Okay, so I think this is probably similar to question number 20.
20. Oh yeah. Yep, I'm sorry about that. I think you have to answer it. We can move on to the next question. From Srikota, does Connecticut DOT have previous load rating numbers for the trusses from past analysis?
That I don't have that information.
Okay. Luis, do you still have time? We still have more, like 5 more questions.
Well, what we can do is yeah, with these 5 questions, or if you receive any questions after this, you can email them to me.
Oh yeah, I think
that's something I'll be happy to take a look at those and get a response back to you.
Okay, yes. So for everyone who asked a question, I will forward all the questions to Luis Vila, and he will reply to me, and I will post it on our blog with the video of the webinar. But I think we can close the session right now. Luis, thank you so much for your time. Thank you so much for hosting the session with us, and thank you so much for using MIDAS Civil for your project. We are so happy, and we hope we can work with you and GM2 Associates in the future and keep helping you and your team with MIDAS Civil software.
Absolutely, thank you.
Yep, thank you so much for hosting, and everyone, thank you so much for joining the session today. I hope you guys can learn something from these sessions, because this session is really insightful, and also there's a lot of knowledge that Luis Vila shared. But yeah, we also have training sessions, weekly training sessions. If you guys are interested, go to our website, www.midasoft.com. You can also check it, or simply email us at grow@midasoft.com. And yeah, Luis Vila, thank you so much once again, and have a nice day, okay?
Thank you all for joining.
Yep, and for everyone, thank you so much. Have a nice day. See you in the next session. Bye.